Ассаламу алейкум, спасибо. Это наш профессор, локальный координатор Дильмурат Хидаврамбеков.
Ну да, здравствуйте.
Здравствуйте, здравствуйте. Я извиняюсь, сейчас зайду в кабинет, будет более-менее стабильная связь. Сейчас я немножко не в стабильной зоне.
Так, если разрешите, можем начать, Дарья.
Да,
Так,
хорошо.
я вкратце объясню, как бы введение, если можно. Меня зовут Хабибулла Насыров, я являюсь координатором Spacecom проекта. И, так сказать, у нас имеется, как я уже сказал, 6 вузов и 2 non-honors. Плюс у нас уже это 4-й день. Ну, если можно, я перейду на английский. Today is the first day of our winter online school within the framework of Spacecom project. And today we have lectures of Daria Stepanova from the Exolaunch company. Her topic is CubeSat technologies. And if you're ready, Daria, the floor is yours, please.
Yeah, thank you very much. So the language will be English, right?
Yeah.
Okay, yeah, great. Very nice to meet you all, and that's a pleasure for me to be here today and share my experience and share my knowledge with you all. I'm gonna start the screen sharing. Please tell me. Just a second. Yeah. So do you see my screen, right?
Yes, we can.
Yeah, great. All right, yes, so regarding our sessions, we're going to have 2 sessions. Today is the first one, and today we're going to talk about nanosatellite technology and their applications. And I will start with some background and introduction of our company, of Exolaunch of German Orbital Systems, a little bit about myself. Then we'll go to the topic of CubeSats, and we'll discuss why they became so popular within last years. After that, we'll go through the possible applications of the small satellites, and we'll see how dramatically the satellite market is evolving and how many more new cool applications there are for small satellites. After that, we will discuss the design specifications, so what we need to take into account while we build in the small satellite. That would be the next topic, building a CubeSat compliant to this specification, and we'll finish today's lecture with the topic how to launch the CubeSat. So we'll discuss possible launch vehicles in the end. I would propose to have the structure of like maybe having 50 minutes lecture and then 10 minutes breaks. So this 3 times in a row. I think that would be comfortable for everybody. If you have any questions, please feel free to interrupt me and we can start a discussion while the presentation. All right, so what's the scope of today? So that's the short introductory lecture about the CubeSat missions in general. So we're not going too deep in detail, but we're going to cover like the basics. And the basic knowledge, what do we need to take into account when we want to build it, and how to start basically with the CubeSat projects. The goal is to give like the first insights and to provide some basic terms and definitions, and we'll go through many examples of these missions. And at the end of the lecture, you will know what the CubeSat is and how to work with that. Actually, I have a question. Have you heard about the term CubeSat? Do you know how to build them and so on?
Yeah, we know what are CubeSats, but we didn't, how to say, start to build them. And so it will be first time because this direction is first for us.
Okay. Yeah, but that's great that you have heard the term. A few words about myself. I'm working at German Orbital Systems at Exolaunch as senior system engineer. I have 8 years of experience in electrical design, 6 years of project management, 5 years in aerospace projects. In total, I was a part of 10 cool projects with total amount of 10 satellites in orbit. I have background in electrical engineering, mathematical modeling, and aerospace engineering. Yes, and I'm basically at ExoLaunch at GOS. I'm responsible for mission design, electronics, and project management. A few words about our team. So German Orbital Systems was founded in 2014, and ExoLaunch was founded several years earlier by graduates of Technical University of Berlin. And since then, we are proposing different solutions for aerospace market. So our portfolio includes satellites, separation systems, and launch service. A few words about what we're doing in more detail. So we provide CubeSat components, CubeSat systems that include pretty much everything what satellite needs for the proper functioning. These are onboard computational modules, batteries, electrical power systems, structures. So together, yeah, transceivers, sun sensors, solar arrays, and cameras. Besides that, we conduct workshops and provide some educational resources. Here you can see that's the flat satellite from one of our projects. Yeah, here's me. And as an example, in 2019, we launched 6 3-unit CubeSats for different missions, starting from IAE's weather monitoring and on-orbit demonstration. Earlier this year, actually, in the end of the last year, we launched 6U CubeSat, so it's a big one, also for weather monitoring and for on-orbit demonstration. Yeah, as you've seen on the previous slides, we are building 3-unit CubeSats, 6-unit CubeSats, bigger satellites, up to 100 satellites. So basically, our customers approaching us with the payloads ideas, and for these payloads we are already developing or adjusting our satellite bus, and we are providing the full service, starting with just consultation, finishing with launch and operations. A few words about the services. So that they include the frequency consultation, that is basically the communication with ITU and coordination process to fix the frequencies for the upcoming launches. Launch services, so with ExoLaunch together, we're offering the launch services for small satellites, technology transfer. These is turnkey solutions, which can actually be extended to full technology transfer program. Basically, we're not just giving the lectures, but also providing in detail how to build the satellite, starting like from scratch. Research and studies. So we conduct scientific studies for our customers and with our customers. For example, right now we're finishing the study with ESA on in-orbit demonstration missions, and we're trying to optimize the approach and the methodology for in-orbit demonstration missions. We have some university programs which give different institutions a chance to work with real satellites in our team. So that includes internships, like starting from 1 month ending to 1 year. And of course, engineering services. We can also like solve customer-specific problems, including hardware, software, ground stations, and also launch. Yeah, regarding the launch service, with the ExoLaunch, we're together providing the separation systems and separation sequences controllers. Regarding ground stations, we have several stations in the Eastern Hemisphere. In total, we can provide the access for S-band, UHF, and some of our partners also provide X-band communication. Mission Control Center for our missions is situated in Berlin. From there, we have full access to our satellites, and we also offer cost-effective mission control center for our customers as a service. Here you can see some cool pictures of our hardware in the test facilities. So we also provide environmental test campaigns, which include thermal vacuum tests or shaker tests. Yeah, so our launch service includes launch of CubeSats of different form factors, starting from 1U up to 16U. At Exo launch, we're providing these launch deployers, which you can see on this picture, which can afterwards be installed on the launch vehicle. Here are some cool pictures from our previous missions and previous launch campaigns. I would like to mention here that we're one of the companies, a few in the world, who are providing turnkey solution, which means that customer delivers the satellite in our office, and since then all the paperwork, which is one of the biggest headaches actually during this all this process. So we're taking it all on us, and making it like really smooth for payload providers, to giving them a chance to launch their payloads and launch their satellites in a like really smooth and flexible way. A few words about what equipment and what are our capabilities. In Berlin, we're having the Class A clean room available since 2016, like almost for more than 4 years. So basically all the works with the satellites and integration into flight deployers is happening in the clean room facilities. Basically, we have all necessary equipment to work with satellites and with launch deployers. Yeah, and for more information, please visit our website and have a look and like more closely at what we're doing. Right, so then after this quick introduction, I propose to jump in CubeSats and applications. Do you have any questions so far? Or everything's fine? Everything's fine, okay.
1 hour is yes, 1 hour is everything's fine. Thank you.
Cool. All right. Yeah, so CubeSats, what this term is about and when it was developed. So here on the left, you can see Bob Twiggs and Georgie. So these are two main inventors of the CubeSat technology. In 1999, so more than 20 years ago, at Stanford University, this concept was born. The idea behind that was to bring educational organizations closer to aerospace technology, to make universities be able to launch their space missions and launch their instrumentation in a more easy and a more flexible way. And what is more important, in much cheaper and much smaller development time. So that resulted as the first release of CubeSat design specification. Today is actually the 14th release already. So what is the CubeSat? CubeSat is the U-class spacecraft. It's a type of this miniaturized satellite for space research and for other space application that is made of multiple cube units. Each cube unit occupies 10 by 10 by 10 centimeters. This is the smallest one. And it's not a tight requirement that every unit has to be not more than 1.33 kilograms, but for every unit, there is a maximum limit, which depends on the launch provider. And often these satellites, they use commercial off-the-shelf components for the electronics and structure to bring the development cost below. CubeSats are normally put into the orbit as a piggyback launch during the piggyback and during the launch of some bigger main payload or from the International Space Station. As of 2020, so until the last year, there were more than 1,300 CubeSats. CubeSats have been launched, and later we'll see the statistics about where these CubeSats belong. On the picture on the left, you can see different form factors. So CubeSats normally start from 1 unit, 2 units is already like a little bit bigger satellite, up to 12 units, and in 12 units it's possible, pretty much possible to fit some like advanced hardware and advanced instrumentation for research, Earth observation, or information technology. There are some projects regarding 16U satellites, and also fractions of 1 unit, which is like 0.5 units, 0.25 units, but these are quite non-standard. So most of the satellites they're looking, like that, like this set of satellites shown on the left. Yeah, I really like this this picture, and it really shows the simplicity and the way the CubeSats methodology evolved. So basically, there's a really small cube which you can stack one onto another, and in this way, you're enhancing the capabilities of your satellites. There are kind of 4 types of missions for CubeSats. The technology demonstration is the one, I think, which most of the organizations around the world are interested in. Scientific research and educational projects, they more belong to university programs, and commercial missions, they include Earth observation, tracking, machine-to-machine communication, and so on. Main advantages of building these types of satellites is the rapid development. Basically, standard time of building this kind of satellite is around 2 years. At the ExoLaunch at the German Orbital Systems, we achieved 8-month development time from like the very scratch, very beginning of the project until the launch and operations. So that really brings the speed down of the development and then the launch. This is a pretty simple technology, so it's possible to buy components from any electronics shop. There's a backside of this advantage is that these components, which are normally used for CubeSats, they're not radiation hardened. In other words, that means that they might be subjected to some failures while on the low Earth orbit or medium orbit. But there are some tricks to mitigate that, and there's also a list, I think, of components already existing, which have been tested in space and which can be used like in other missions. This CubeSat is simple to design. Sometimes actually the trickiest question is how to fit everything you want into this such a small volume. But when you don't have much space, you cannot put a lot of stuff inside. So it's relatively simple, and that's why it became so popular in universities projects. With the space debris, it's also a trick question because taking into account the fact that most of the CubeSats are launched into low Earth orbit, which is like around 500, I think, is the favorite orbit for the small satellites. They can burn up in the atmosphere upon re-entry. Yeah, so average decay time for the CubeSat is around like 20 years, which is still good compared to some like graveyard orbits, like much higher, where the satellites and the rocket parts are just floating there and will be floating forever. So on one side, CubeSats are facing the question of space debris due to the fact that there are so many right now, but the decay time is still acceptable. And low cost is the outcome of the fact that there is a simple commercial off-the-shelf components are used, and on the other side, the fact that the launch provision has been simplified by the introduction of these deployers and specific dispensers for these types of satellite, makes it really, really cheap compared to big and complex satellites. Regarding the orbit, yeah, so I think the most attractive orbit for the satellite starts with around 400. It's almost the same as International Space Station, and ends up somewhere at 600. As CubeSats are not primary payloads for most of the launch vehicles, CubeSat providers do not normally choose the orbit they want to fly. So launch providers give a set of the possible orbits where the launch vehicle is going to go within operations, and CubeSat providers can choose which orbit is more suitable for them. A few words more about the fathers of the CubeSat technology. So Bob Twiggs was professor of Stanford. He actually founded the Space System Development Laboratory at Stanford. So that was he was the big professor. And in late 90s, 1999, he came up with this CubeSat standard. And Georgie, he was also professor, but at California Polytech University. Later, he became the Tyvek nanosatellite CEO and founder. Before he came up with the CubeSat design specification, he participated in different satellite projects, and I think that was his inspiration towards the development of this standard. And in 2011, he founded the company called Tyvek. Yes, so what's the main purpose behind the CubeSat design specification is to provide access for small satellites. And as it was mentioned, it was published in late 90s. And the first CubeSat based on this specification were presented on international conferences in 2001 and launched in 2003. The first satellite was separated also in 2003. And it was, pretty much the first mission. Here you can see the first orbital deployer, which was called P-Pod. This kind of deployers were used for the CubeSats back in the days, so like 90s and early 2000s. Here on this picture, you can see the CubeSat. It's integrated inside, and this instrumentation is later integrated into the frame of the launch vehicle at the moment in the orbit where the satellite shall be deployed. The command from the launch vehicle is sent to this kind of deployer, and the satellite is ejected into aerospace. So the first deployers were quite small and not so advanced, and these are the deployers we are providing today. So yeah, this is the deployer for 12 units in total, and it can be configured for 12 1U CubeSats, or for one big 12-unit CubeSat, or for the combination of 6 units and 3-unit satellites. And on the left, these are the deployers, but for the tests, basically prior to the launch, it's possible to integrate the satellite into this deployer and conduct tests on the shaker table. The simple representation how it was before and how it is now. If before it was required to build a big satellite, and there was no option to piggyback, almost no option to piggyback the satellite with another launch. So today, this like frame adapters, which are installed instead of this satellite on the last stage of the launch vehicle, are used, and it's possible to surround the frame with a bunch of these deployers in total, making like 70 satellites launch per one mission. A few words about specifics of CubeSat missions. Some years ago, these types of missions were mostly conducted by university, with a strong emphasis on education. As you might notice, as the price and as the development time of the satellite was reduced dramatically, it's like really attractive to give hands-on experience for students in the universities to build this kind of this satellite. However, it has been changed. Today, the majority of CubeSat, they have commercial background, and most of them are dedicated for IoT to constellations, to remote sensing, to communications, and the big parts still left for technology demonstration. And here we're starting to talk about the applications of CubeSat. Having the information I just presented, I just want to make it a little bit more interactive. Do you have any ideas of which applications might be used for this kind of technology? Please, like, don't hesitate to raise your voice.
Okay, so for this, we can do everything. Only satellite communications will help us. And I don't know, it will be very great.
Okay, any other ideas? Somebody wants to join it? Discussion?
Okay, any others? Если даже на русском можете присоединиться. If you agree. Дарья.
Не стесняйтесь, если есть какие-то идеи, давайте.
Так,
Alright, I will not be pushing, it's okay, yeah.
Не, у нас просто многие позже подключились, поэтому, наверное, чуть позже они присоединятся.
Ну, хорошо. Ладно. Alright, yeah, then I'll continue. So yes, there are a lot of different applications for CubeSats nowadays, and all these beautiful pictures, they visualize what CubeSats can be used for. The first and the biggest one, I think it's Earth observation. So the biggest constellation of the small satellites up to date, of CubeSats up to date, it belongs to a company called Planet. So the Planet's idea is to make pictures of the Earth with a revisit time 24 hours, basically. They're picturing the Earth, all Earth, every day. So with this amount of data, like within time, it makes it possible to see the changes, like in like really different aspects, starting with like vegetation, agricultural changes in the soil, how ocean is moving, how like water is changing, and so on. Another one is synthetic aperture radars. So this is the satellite dedicated for SAR imaging. If we're talking about Earth observation, we are mostly thinking about visual spectrum or infrared. When we're talking about SAR, these are radio frequencies, and it makes it possible to picture Earth in different radio spectrums and to also gather information in different radio spectrums. And that's also can bring like enormous benefits when we're talking about such fields as agriculture, maritime, and so on. The next big application is cargo and tracking of goods, and basically like machine-to-machine communication while like big ships are moving in the ocean. There's no communication for them using the network, like the standard network we all used to. So the satellite communication using the constellation of small satellites can make it possible and make it much more cheaper than using existing solutions for communication. Here it shall be mentioned that not only ships, let's say, tracking, but also it's possible to track separate like cargoes, which is also like really attractive for like some bigger companies. In other words, when you are sending the package from one place to another via ships, you can track exactly like your container and not just like the whole ship. Navigation and positioning is one of the like topics to discuss regarding the small satellites. Then interplanetary missions. Here it was like last year there was the CubeSat launch. The CubeSat launch was launched, the one which went to the Mars, and there it was the NASA mission. There NASA demonstrated that small satellites can like be really used and be really useful while interplanetary missions. So for example, as for that mission, it's called Marco mission. The small satellites were used as a retranslator for the main spacecraft. Yeah, Arctic monitoring and sea monitoring, fishing monitoring. It's like a lot, all the possible ways of monitoring the Earth makes it much more attractive with the use of constellation of small satellites. Like again, as fires monitoring and fast response to some natural disasters. We've already seen, for example, with the use of these planets, CubeSats, that really fast and really like a quick response to natural disasters can like already save a lot of resources on Earth regarding like the elimination of these disasters. And machine-to-machine communication, basically everything is currently trying to be connected to internet and diversifying the communication capabilities of our like vehicles, of our devices using the low Earth orbit constellation network is also looks like a big step forward. All right, yes, that's the one example of cargo tracking and receiver of information signals. So here on the left you can see the cargo, the big cargo ship, and on the right you can see the tracking of the movement of this ship and of this cargo. So it's pretty much possible to get in information about the how the ship was moving in the ocean, or in the, here you can see like it's Middle East trajectories, and to track the ships. It's possible also to track airplanes. Basically, that's a super cool use case because when the airplane is traveling like through Atlantic or like any other ocean, and there are no ground stations to track the position of the plane. And basically, when planes crash, nobody knows where is it in the ocean. That's due to the fact that while airplane is traveling from one side to another, nobody really knows where it is. So ADS-B tracking of airplanes is also a huge potential field for CubeSats applications. And hyperspectral imager together with SAR and together with like standard optical imaging can serve in the, first of all, agricultural, in the forestry monitoring, in the water monitoring. Then here on the left you can see different layers of hyperspectral imaging, and on the right, in the way that they are absorbed, it's possible to see mixed vegetation and soil, water layers, soil and rocks layers. So basically we're filming the Earth in different layers like onions, and there with the hyperspectral imager it's possible to withdraw information about every of this layer and to make a conclusion what happens in this layer. All right, and here we come to some statistics and what's been in the past and what's the predictions in the future. On this plot, you can see the statistics of the CubeSat missions starting from the very first one in 2000s and with prediction until 2025. In the green, you see the already launched satellites into orbit, and red are launch failures, blue are announced, and the gray one is the actual prediction for the next years, depending on like what entities have announced the fact that they're going to launch their satellites. Basically, the early 20s, while the first CubeSats were built and technology was evolving, but there was not so much, there were not so many launches, and like everybody was just getting used to the fact, getting used to this new technology. However, in 2012, with the first commercial, especially companies noticing the trend and facing the fact that it's becoming much cheaper and much faster to build and launch the satellites. The amount of CubeSats has been growing every year. So yeah, 2012 there were already 25 satellites on orbit, while in 2017 there was the maximum of 297 satellites launched. Since then, the number has decreased slightly. That is due to the fact that the biggest constellation provider of the small satellites has already deployed the constellation on LEO, and the only thing they're willing to do in the next years is to support this constellation, meaning they do not need to launch like 100 a year. They need like to launch around, let's say, 15 only satellites per year. And that was happening like to several constellation provider, to like Planets and to Spire, I think, as well. However, based on the announcements and predictions, the number of small satellites is going to still be growing. Yeah. There are a couple of reasons behind it. The first one, as we've already heard, the attractiveness in terms of costs and schedules. The second one is the fact that there are pretty many new launch vehicles developing right now. And there might be more options for CubeSats to be launched, and the price might even go even lower within upcoming years. Here you can see the statistics based of satellites launched based on organizational type. In green, you see the launched ones. In blue, not launched by announced. And the trend is purely commercial, with almost double the size of universities launches. So they were already 422 satellites launched by companies, and half of them, actually more than half of them, belongs to constellation providers. On the other side, universities have launched 286, which is also like pretty big number of satellites. Agencies are less interested in this market because yeah, there are a couple of reasons behind that, and one is I think is that agencies are much slower in terms of decision making towards like innovative solution than like companies and universities. Military wise, the biggest portion is belonging to the US military satellites, and like as for others, you can see that institute non-profit schools have like not so many satellites launched. There are also one individual satellite. There was somebody who decided to make their own satellite and to launch it, and independent belongs to like some independent organizations. On this map, you can also see the distribution of satellites by country, with the US beating, I think, everybody else together, launching more than 1,000 satellites, like in total. Regarding the status of launched nanosatellites, more than 800 are still operational and still generate the scientific data and they provide scientific outcome. 200 satellites are not operational anymore, or they were not since the beginning. 338 satellites have re-entered the low Earth orbit and like the atmosphere of the of the Earth, and 93, which is like quite a big number, were not launched and were not tested due to the launch failure or deployment failure. Here you can see on this plot the number of orbits, like the orbit distribution per launch. And we briefly have discussed that like earlier. The most attractive orbit so far is 500 kilometers, 97 degrees polar orbit, sun-synchronous. That's, yeah, basically where we have most of the satellites Then going left and going right, the smallest orbit was 200 to 150 with 51-degree elevation, inclination. Sorry, and I suppose the satellite re-entered quite quickly. And the furthest orbit was the Mars flyby in the deep space. That's these 2 satellites in the Marco mission. There were some attempts to launch satellite in high orbits, for example, 750, 800 kilometers. There were like 9 satellites for that, and to GTO orbit. There were also 2 attempts to launch the satellite. As we can see, the fastest satellite to decay, like the lower the orbit, the faster satellite decays, and taking ISS orbit and taking all the satellites launched to the ISS or from ISS, in total 296 satellites have been decayed. Constellation-wise, on this plot, you can see the companies which are aiming to launch the constellations or to deploy the constellations in the near future. In green, you can already see satellites which are launched. They are not necessarily all in orbit right now, but yes, so these are already launched satellites, and the blue are planned and not announced. So on the left, you can see the Planet company, which is doing the Earth observation with total amount of 427 satellites. The second biggest deployed constellation belongs to Spire with total amount of 117 satellites and 33 satellites planned to be launched. And Helios-Spire is the next one with total amount of 45. However, as like you can see in the plot, many companies have really ambitious plans to cover the low Earth orbit and like general orbits with constellations, and with all this amount of satellites, like it's going to be like really crowded. I foresee in the near future. By types, so yeah, we saw at the beginning that there can be different types of small satellites, starting with 0.25 unit CubeSats and up to 16 unit CubeSats. There are also some other types of satellites included, for example, like really non-standard 8U satellites, or like other nanosats like picosats or nanosats with a weight from 1 to 10 kg, but are not necessarily following the CubeSat design specification. And by year, we can acknowledge that the industry was evolving based on the smallest CubeSat form factor, which is 1U and 1.5U. Here you can see the orange and the yellow, like this orange color is dominating. Once in 2013, Planet started the deployment of its constellation, and like other companies noticed that 3U, like companies and organizations noticed that 3U is more advantageous CubeSat form factor. The green one belonging to 3U CubeSat form factor started dominating the statistics. Within the time, so like I think since 2019, some more demanding applications of CubeSats, such as synthetic aperture radars or some advanced imaging payloads, with the development of this instrumentation, it became like companies started requiring higher, like bigger satellite form factors, and there's 6 units and 12 units and 16 units. CubeSats already been launched, like more of them have been launched. And as for 2021, based on the prediction, the biggest amount still will be belonging to 3-unit CubeSats, while 6-unit CubeSats will be in the second place. And already 16U and 12-unit CubeSats will reach almost 100 satellites to be launched. This is also a cool plot. This belongs to amount of companies which have been founded in nanosatellite industry since 1990, and we can like see how fast the sector is like developing, while the trend actually started in 2011 and 2012, when some of the companies like which were in frontier has shown that this approach has lots of benefit. Every year there are like more than 40 new companies, which brings us to a little bit of concern that the overall nanosatellite market is expanding quite quickly, and there might be some like consolidations and some reformings in the near future. So there are quite a lot of companies right now, and some experts are a little bit concerned regarding the market sizes. And here you can see the example of how many companies are launching different types of CubeSats and providing platforms and mission services. Yeah, I think here my first part of the lecture is finishing. We can make a like 10 minutes break, and then I will start with a cool table. Like I will show the table with some really interesting insights. Is that fine?
Oh, sorry. So is there any questions?
Yeah.
So I have one, if you don't mind, about launching and how to say it, making some CubeSat. About price, can you share with us your experience? How much will it cost? So, for example, CubeSat of the, not so small, but like a medium-sized CubeSat with just simple tasks, just like a navigating or just taking pictures, a very small resolution. How much will it cost, and launching it?
All right. Regarding this, the price, it really depends on the payload. It really depends on the like mission scenario and operations. So, like how much engineering efforts will it need to update the payloads, the platform for this specific instrumentation? I think the average price is around 100 for 3-unit CubeSats to develop it. Regarding the launch price, it also really depends. Like here, I might not give you an answer because we're talking with each customer independently. This depends on the launch vehicles. So, for example, American like Falcon and Soyuz, like Russian Soyuz, they have like really different settings while providing these piggyback solutions. Or Indian one, some care about the volume more, some care about the space more. So that also depends on the form factor. So obviously 3 units will be cheaper than the 6-unit CubeSat. So that's a tricky question, and this shall
no. For example, not exact price, but from something till something, like because I know this is not. If you say some, for example, 100,000, and I will pay you, and I will ask you just to launch. No, just like how to say the beginning price, and I know the maximum is not exist, but the cheapest price, what could be? For example, we have fully how to say equipped rocket, and we have very small piece of the free space, and we are manufacturing for that exact place, and just putting our CubeSat to that very little one and launching. The minimum, how much it could be?
Yeah, okay. So regarding that, it also starts from around 100. to
So
launch.
manufacturing 100K and launching also could be
Around,
100K.
yes. It can be also cheaper depending on the conditions, but like I would say,
Yeah, maybe like how to say, like in tourism, like rush hours or something like that, when everything is already booked and you can just join to that place. So
yeah,
it could be cheaper. Yes.
yes.
Great. Thank you. So any other questions?
Good afternoon. Let me say good morning to Europe, to Germany. Thank you very much, Daria. This was very nice explanation of CubeSat. We are very excited. My question is, do you planning or have you already launched CubeSat for scintillation monitoring?
Thank you for the question. For what exactly monitoring? I didn't hear.
Scintillation.
Scintillation.
Yes.
Maybe
Yes.
I'm not getting the word correctly.
I mean, when the signal coming from a satellite to the Earth, they are coming through the, let's say, the atmosphere. There are the signal, let's say, the ionizing. Then this process called scintillation.
Scintillation. Okay, I didn't hear the. Yeah. Right. So we like at our company we didn't launch the satellite for that application, but there are some like Helios Wire, for example. They're doing that, and there are some other companies, I think. Yeah, so that's also quite big field for atmospheric monitoring. Yes, but there are satellites like that.
Okay, it means that the CubeSat, I mean the
CubeSat, yeah,
this
CubeSat can carry this instrumentation.
kind of process in their application now.
Yeah.
Okay, thank you very much.
Yeah, thank you for the question.
Okay, so 10 minutes, is it enough?
Yeah.
Break? Okay. So we'll have 10 minutes break. The Doom will be stayed. Okay.
In technological advancement of these companies. So, for example, in the field of machine-to-machine AEs on IoT, there are like, as you can see, several companies running that. Some advantages. Some advantages include that, for example, Orbcom is 100% dedicated to machine-to-machine applications, which means it's gonna connect satellites. Using the satellites, it's gonna connect different machines, different vehicles in the globe. The constellation size is around 52 satellites. Then interesting project is Helios Wire. This is they're gonna use S-band spectrum to receive the data from the Earth, and with that they're gonna do the frequency mapping. That's one of their application. Swarm technologies, they are based on actually like really small satellite sizes, which is 0.25 units. Gonna be dedicated to two-way communication with small satellites. Like, it's pretty crazy project, and they had like lots of troubles with frequencies. Yeah, I'm not like we'll see how it will go for them in the near future. Then Lacuna Space, for example, they're also providing machine-to-machine communication and so on. The second big trend, as you can see, is the Earth observation and Planet, launched since 2013 with total amount of 427 satellites. With sensors that they are providing, they can go up to 3.7 meters ground resolution with quite a big swath and the major satellite altitude is 475, which means that satellites decay within like a year or several years, which makes it for them necessary to launch other satellites to have the full constellation kind of covered. Regarding Earth observation, there is also Reactor Space company. They're doing hyperspectral imaging besides normal imaging, and yeah, Hera and so on. If we see on the third most popular application, it's like weather, AIS and ADS-B. For example, this is for Spire. They're measuring the GPS signal. That's I think what we've also had a quick chat before. So I mean that's a little bit other technology, but close to that. Changing in GPS signal passing the atmosphere and predicting the weather, how the weather is going to change regarding temperature, pressure, and humidity. The Harris Corporation is also dedicated to weather monitoring with 12 satellites. They would like to map winds in 3D over the Earth. And orbital microsystems, for example, they also aiming to capture the temperature of the Earth, so that they're going to map the temperature around the globe. And Synlabs, for example, interesting applications, the RF spectrum monitoring. So that means that I think the major application field for them is to search for illegal ship fishing and illegal activities in the ocean. Basically, if there is an illegal ship in the ocean and it emits some radio signals because it needs to have some means of communication, and with the use of the Unseen Lab service, it would be possible to detect the plate and position this illegal vehicles and more precisely like ships. Yeah, so there are some like really exotic applications, for example, like optical communication. The Spacecom, the company has been just announced. They're planning to launch their first satellite in this year. They did not decide upon the constellation size. However, they're aiming to provide quantum communication, like really secure communication using the small satellites. Yes, all right. That was regarding some commercial CubeSat applications. I think the cool thing is to see the crowdfunding numbers. There were a couple of nanosatellite crowdfunding campaigns. Actually, there were quite a lot, and we can see how the goals were achieved. So, for example, me personally, I like the Andurasat the most, I think. So they raised 100,000 K for building the satellite based on Arduino platform, and they have launched it. The satellite was working on orbit, and since then, after this successful launch, the company shifted to other markets and became Spire, and now they're having their own constellation. I think the most successful was her kite from Planetary Resources, was $1.5 million in 2013. Yeah, to take selfies from space using the small satellites. Like, okay. Also like pretty exotic application. Then yeah, you can have a look afterwards to different crowdfunding campaigns and to see how crazy can be people about the applications of small satellites. Regarding technologies, I would also like to show a little bit of some advanced technologies small satellites are carrying. Regarding communication, there are quite a lot of companies providing communication services and giving communication payloads out. So there are a lot of advanced instrumentation from NASA, especially for interplanetary CubeSat missions. As we talked about this Marco satellite, it was carrying the huge X-band panels with almost 30 dBi gain for deep space communication. There are also like other types of high-speed communication, which K-band, X-band, which can achieve up to 200 megabits per second and 500 megabits per second. Right now, there's also a hot topic for small satellites, the optical communication, and there are, I don't see them here in the table, but with the use of optical communication, it's possible to achieve like gigabytes per second. And for small satellites, this technology is still under development. Power-wise, some advanced deployable solar panels or some advanced lithium-ion batteries. Also, like you can see some examples of different payloads and different instrumentation. Regarding propulsion, there are also quite many companies which have been founded last years, which are working on like different types of propulsion with different propellant, like in general, starting with non-propellant like solar sails or like nanotrusters with liquid metal or electrosprays. All right, so that's like I highly recommend this source. You will find like a lot of data for inspiration and for like in general, if you want to know more about the missions, about companies, and about like the background, that's the really nice database for that. And I'm going back to the presentation. Yes. And we start with CubeSat design specification revision 14. I hope it's not going to be too boring because we're going to talk about requirements and standards. The CubeSat design specification is basically the document which describes what guidelines and what requirements shall the satellite follow. It's not as defined as might be a document for a bigger satellite. However, like based on my experience, some customers still can get some troubles with these requirements. And I will tell a couple of fun stories in the end of this session regarding the troubles. All right, so there are some of them general requirements. So the first one is basically CubeSat shall incorporate some like shall submit some reports in terms of following these requirements to the launch provider. Yes. So all parts shall remain attached to the CubeSat. It's not possible that something is being deployed while the launch. There shall be no pyrotechnical devices inside the satellite, and the satellite shall not generate additional space debris. No pressure vessels over 1.2 atmosphere shall be inside the CubeSat, and the safety factor shall be more than 4. Total stored chemical energy, if we're talking about like batteries, shall be less than 100 watt-hours. Satellite shall not include any like really hazardous materials. Satellite also shall satisfy the following, like this outgassing material, that total mass loss should be less than 1%. And regarding this, most of the CubeSat providers are doing the bakeout during the satellite testing and satellite preparation. That happens like in the environmental chamber where the satellite is baked, and what can get outgassed gets outgassed. However, this requirement might be even tighter for some optical communication, like optical payloads, But that's already on the side of the payload provider. So that's like their business and their problem. Collected volatile considered material shall be less than 0.1%. And that's basically that's all written in the specification. There are a couple of things which are required to have in mind. That's the coordinate system orientation is one of the main ones. Configuration and physical dimensions. This is the place where some of the CubeSats have problems. They shall really follow the dimensions, otherwise it might not fit into deploy or might be too loose in deploy and it will be shaken during launch. So on the 1U side, it shall be 100 millimeters wide, and the tolerance is plus minus 0.1 millimeter. Basically, this is the dimension between like major rails. Then the single dimension is already 113.5, triple is 340.5, and there it's a little bit bigger the tolerance. Regarding the components which are expanding from the rails, there is a place of 6.5 millimeters where some additional instrumentation, like sun sensors or payload sensors or some deployable sonar panels can be stored. External components shall not contact the deployer, otherwise the satellite might have troubles during the deployment. Rails is the main mechanical interface between the CubeSat and the deployer. And basically, from the mechanical perspective, the most tight requirements are put on these rails. So their minimum width shall be 8.5 millimeter. It's really important to have correct surface roughness of less than 1.6 micrometers. Otherwise, there might be some unnecessary friction between the rails of deployer and the rails of the CubeSat, which might also make it difficult for the satellite to be deployed. Edges shall be rounded at least 1 millimeter radius. Z plus axis shall have minimum surface of 6.5 over 6.5 millimeter square. At least 75% of rails should be in contact with the rails. That means that if satellite is too small and is too loose in the deployer, it's also not acceptable because of the internal vibrations of the satellite during the launch. 25% of rails may be recessed. That's about rail contact of single and triple satellite. Regarding the mass, single CubeSat shall be less than 1.33 kg, while triple CubeSat shall be less than 4 kg. And based on my experience, it's really hard to make them be harder than that. So as most of the components in such small satellites are electrical, like PCBs do not weigh more than total amount of printed circuit boards cannot weigh more than 1.33 kilogram for a single CubeSat. Center of gravity shall be located within 2 centimeters sphere around the geometrical center of the satellite. This is kind of pretty hard to track this requirement. However, when the overall launch vehicle ballistic analysis is conducted, this requirement is taken for the overall launch vehicle as a basic. It's not so strict in reality, and some deployers can handle a little bit more of this deviation. However, if all the satellites will have in one container, we have geometrical center deviated to one side, that might become a problem. So it's better to keep the gravity in the center of the satellite, especially when we're talking about active attitude control. The closer the center of gravity, the center of mass to the center of gravity, geometrical center of the satellite, the easier it is for like different maneuvers to be conducted. Regarding materials, aluminum of like 2 alloys are the most common for structure and for rails. For structure, aluminum 70-75, and for rails 60-61 is used. Rails and standoffs shall be hard anodized to prevent cold welding. In other words, we do not want the satellite to stay in the container due to the welding. That's why there shall be no like conduction between these two components. Separation springs shall be on designed rail standoff, shall be placed either on the side of the rail or in the back of the rail. This separation spring, basically is the one which is touching the rails during the satellite deployment. And it also has to have like some defined like 0.05 inches above standoff. And this is not like a really tight requirement for 3 CubeSats. It's more for like, it's for 1 unit CubeSats when they're together, like in 3 unit deployer. The separation spring helps to separate the CubeSats one from another. Basically, like maybe I will repeat it once again. For 1 unit CubeSats in the 3 unit deployers, like all these 3 CubeSats are accommodated inside this deployer, and there is a separation spring between them. So these are the requirements for this separation spring between. And as the 3 new CubeSat is occupying alone all the space in this deployer, there's no need for these additional requirements. All right, this is the basic drawing for the 1 unit CubeSat, which every CubeSat manufacturer shall follow. Here, basically, you can see the sizes, geometrical sizes, the tolerances, and so on. From like, yes, different perspective. Basically, rails, contact rails for the on the sides, the places for deployment switches. The red ones are the deployment switches, and these ones are separation springs. A few words about deployment switches. So basically, when the satellite is in the deployer, it shall be powered off, not to influence any other instrumentation on the launch vehicle or in the deployer. Basically, these deployment switches are aiming to shut off the battery from all the satellite. And they work in the way when the satellite is in the deployer, these 2 deployment switches are pressed. And as soon as the satellite is deployed on orbit, they are pressed. And by that, battery is connected to the main electrical power system and satellite is turned on. All right. Besides the geometrical, like main geometrical dimensions, there are also 2 access ports located on the both sides of the CubeSat. What are these access ports? Basically, after the satellite is installed into the container, it is still possible to get an access for like last verification, last checks on the launch side. For that, one of the windows of deployers can be like taken out. It's a small window, and with taking out this window, it's possible to get an access to this green area. It is possible to place here, for example, the connector. We call it EGC connector, electrical ground support equipment, and to make last preparation of the satellite, which is like charging the batteries, checking the software, checking the state of the systems, and so on. So yes, this is the major CubeSat specification from mechanical perspective. This picture is also taken from the CubeSat design specification, explaining how big in units can CubeSats be. And from here, we go into some electrical requirements. They're not so many, but still there are some to remember. There shall be no active electronics during launch. So battery or CubeSat with battery shall be fully deactivated or discharged. Discharged is not the best idea. Probably most of the people, most of the CubeSat developers want the satellite as soon as it is on the orbit to start working and to start like functioning properly. For that, the CubeSat battery is detached using these deployment switches I've just talked about. For that, minimum one deployment switch is in designed rail shall be placed. So the best is to have 2 deployment switches on 2 rails. All right, to bring some kind of redundancy, and in terms like if one deployment switch is failing, this is a really critical requirement, so it's better to have like some additional instrumentation for that. And during the launch, all systems shall be turned off, even including real-time clocks and like everything else. Yes, to allow diagnostic charging, all connectors shall be at access port locations, and this is this requirement is about this access ports. Basically, if you want to follow, like if you want to have an option to get access to the CubeSat, you can follow this. If you think it's not as important, it's possible to ignore this one. However, like, there might be some situations on the launch side when it's better to have an access for the satellite. CubeSat shall include remove before flight pin with or be launched with discharged batteries, which is like in most cases not the best idea. Remove before flight pin shall be removed after the satellite integration into the deployer. So basically, how it occurs, the satellite on the launch side, or for example, once our customers bring satellites at our facilities, the satellite is turned off. And as we have noticed, there's a way to turn on the satellite pressing the deployment switches. There's also another way of separating the battery from all the satellite subsystems is using the remove before flight pin. Basically, it has the same functionality. It detaches the battery from the system. So once the satellite is ready for integration, the remove before flight is installed. Most likely it's actually installed during the transportation, because like we don't need the working satellites during transportation from the customer's facility to ours, especially like we don't want to consume the battery or the satellite to operation on Earth. Thus, after the satellite arrives to the integration facility, it's been like everything was prepared, satellite is integrated, satellite is turned off, then the door of the container is closes, and at this moment it's important to not to forget to remove before flight pin. This is done through this access port location. Yeah, so it also cuts all the power from the satellite. And remembering the requirement, like mechanical requirement from this 6.5 millimeters extrusion from the rails, it shall also not be higher than that in order to get like satellite into deploy with remove before flight pin installed. Some basic operational requirements: CubeSat with batteries shall be able to be shut down by transmitter command. This is in case there are some troubles or there might be some legal troubles. For example, with this 0.25 unit swarm technologies, there was a big story when they did not file the frequencies correctly, so they had to be shut down because they were not following the specific rules to get these frequency allocations. So there shall be some kind of tool to shut down or to shut down the satellite with a command over radio. Deployables shall wait until at least 30 minutes after ejection. This is also the safety rule. While after the ejection into the orbit, there might be like that. So the satellite is not the only one deployed. There normally like 10, 50, or like 100 small satellites can be deployed more or less at the same time. And if some of the satellites had like a really big deployment, for example, a sail or like a big boom or antenna or solar panels, and not enough time has passed for satellites to get spread, there might be some collision. So it's better to wait for some time until satellites are a little bit spread in the orbit to conduct this deployment. The same is connected to radio frequency transmitters. So all the transmitters with power more than 1 milliwatts, which are basically all transmitters, shall wait at least 30 minutes after ejection. This is also, this requirement is also not to damage the transmitters of like other satellites while like after, like right after the deployment there. The satellites are pretty close and pretty dense to each other, and after 30 minutes, they can be already spread. Operators shall obtain and provide documentation proper to frequency licenses. And if we're talking about amateur frequency licenses, as UHF, which is I think the most used frequency for small satellites, there shall be a proof of coordination by IAA-RU. And some companies, as I just mentioned, can have troubles with that. It's better not to play with frequencies. Orbital decay time shall be less than 25 years after end of the mission. And that's like, obviously nobody's also gonna, like, it's pretty hard to estimate how, it's possible to calculate how fast the satellite will decay. And this is, decay lifetime is a critical requirement once we're talking about the space debris. Having in mind the amount of satellites which are planned to be launched in the constellations within upcoming years, this might be a critical requirement for the next missions. Yes, so regarding the fit checks and deployer integration, there shall be a final fit check before the launch. And basically, like our customers are bringing satellite dummies in our office before the final satellite integration into deployer in order to fit check the geometrical dimensions. And sometimes it happens that the satellite is not fitting due to like this dimensional differences between requirements and actual sizes between the rails, which is kind of pretty sad. At least if it's done before the final satellite integration, it's possible to like still change some rails dimensions and like either reorder the structure or work the structure out. For that, CubeSat acceptance checklist shall be used, and this checklist you can find in the CubeSat design specification documentation. Regarding the testing must confirm all launch provider requirements, and this really depends on the launch vehicle, as different launch vehicle have different loads, different like vibrational profiles, and prior to the launch, like it's important to check them out. At ExoLaunch, we're also providing the test service. Basically, the satellite can be delivered to our facilities, and we have partner companies here in Berlin where with like big shaker tables where it's possible to conduct tests with all the launch providers we are working with. Right. If launch vehicle environment is unknown, there is a standard which is used for testing requirements. And regarding testing requirements, it's also, I think, important to mention that The satellite itself shall not strictly follow the requirements, like the vibrational requirements of the launch provider, as the satellite is placed into the deployer during the launch. The deployer takes most of the loads for itself, as the satellite is fixed in the container in the deployer. So the deployer, this connection between deployer and the satellite, it dampens some of the frequencies, and it changes the frequency profile with actually like bringing amplitudes of frequencies, like amplitudes of vibrations lower. So there are different tests which are called like acceptance tests, protoflight tests, and depending also on the launch vehicle, it's possible to conduct like one of those tests prior to launch. A few words about specifics of CubeSat missions. So university CubeSats are usually designed within 3 to 4 years. That's enough time to conduct the research, to build the platform, modify the platform, to conduct all the tests, and 3 to 4 years is for some student projects exactly the time where like during the bachelor or during some years of the master, students can like participate and to observe the biggest part of the mission. So undergraduate and graduate students participate actively in the development of the satellite during these 3 to 4 years. Commercial CubeSats are usually designed from 1 to 2 years, and that depends really on if the company has the platform, or does the company need to modify the platform for a specific payload. And typical teams consist of like 18, 12 engineers for an average mission. At least partially CubeSats, at least were designed from scratch. And I think today there are like just so many companies providing platforms and providing solutions which are ready. So there's kind of no need anymore to design the satellite from scratch. And especially for the university, I think it's much more attractive to come up with some advanced instrumentation and advanced or like interesting payload, and then just buy the platform which has been flown, which has shown its reliability in past missions, and like maximize the scientific outcome by focusing on the payload design than on developing like some new CubeSat platform from scratch. Yes, so more than 60% of all CubeSats that reached orbit remained operational for more than 6 years, even though the design lifetime is 2 years. This shows that most of the CubeSats that are failing like either from the very beginning or not failing in a long time. Like low Earth orbit is not so aggressive regarding the radiation. There, like it still is, but most of the commercial components can successfully work for a longer time than just 2 years. All right, then we're jumping to the CubeSat design philosophy, and here we're gonna talk about how do we work with CubeSat projects, and how do we address the question of building the CubeSat like platforms. There are kind of two types of philosophies. First one is to design to objective, or the second one design to cost. First one is based on the goal of the mission. So if you first come up with the goal of the mission and the goal of the payload you want to have on the satellite, and through the first things to determine is expected environmental conditions. On that stage, already hardware shall be appropriately designed and selected for mission objectives. And new designs must be generally tested against environments. In this case, time might not be the critical parameter. However, not as in the second philosophy where design to cost. Here the project cost is fixed, and with a fixed cost, the team shall define what is possible to achieve, which objectives and which goals. Component selection is normally driven by costs, not as design to objective, where it's possible to choose like hardware which is deviates maybe in terms of cost from the minimum like budget. Mission objectives and requirements are often subject to change due to affordability. Few words about design to objective. So at the beginning of the project, we have the mission idea, which is later in the program segment split between mission objectives and mission constraints. As constraints, there are costs, resources. They can be also like availability of engineers or like ground station infrastructure and so on. From the mission objectives, there are two types of major requirements. First is operational, the second one is functional requirements. Operational requirements include like mission operations, and this is connected to like ground station infrastructure. Functional requirements include orbit. Do we use a constellation, which are orbital parameters, and so on. So that's on the program segment. All of these questions are announced. So orbit, constellation costs, and some other constraints, they bring us to the launch element, and here the launch vehicle, the launch type is selected. Orbit and constellation also, like, and all these constraints, they also define the space segment. Here we define what's the size of the CubeSat shall be, what are the main parameters in terms of electrical power, in terms of like communication requirements. And with this satellite space segment defined and with mission operations in mind, we need to define a communication architecture. And this involves the ground station architecture together with mission control and so on. That's this is the approach while designing, having the objective in mind. Yes. So that's yeah, maybe like a few words. When we're talking about design to objective, we of course have this like, we cannot define it without having the cost and other requirements. And most likely, like the launch element is selected a little bit afterwards, while in the design to cost, cost is the major driven requirement, and launch element, as we discussed earlier, it can be like pretty much the parts, the half of the satellite cost in the end. It's a big question to address. So like in the very early stages of the design. So this design to cost became one of the most used and one of the most like basically most of the projects regarding CubeSats are driven by design to cost methodology. And radical cost cutting can actually reduce the system reliability and performance to the level where it's actually dangerous to, or not dangerous, doesn't have sense to launch the CubeSat. There are a couple of components which is better not to cut costs on, which become the most expensive parts of the satellite in the end. These are the solar arrays, and even lowest budget missions, they use space qualified solar cells. Yes. Regarding the batteries, battery is one of the most risky components, and it's also due to like environmental conditions, the temperature there can get like pretty low, which is crucial for batteries operations. Thus, it's also necessary not to cut costs during the batteries development. And communication system is the third crucial component, where it's better to invest additional resources into the development to have stable communication line with the satellite. Quality assurance while designing to cost methodology is actually also a critical component of the overall design. So it's better not to save too much when it comes to quality assurance of electronic components design or software. So the interface control, mechanical testing are the most important things to do during the satellite development. And especially if it's possible to outsource some job, like for example, harnessing development, it's better to do so to leave some space for more testing. Some approaches look more expensive, but some of them like help saving some money in the end. So for example, buying subsystems can be cheaper than developing your own ones, and it can be also more reliable for them. Like it can be better for the mission to buy some components which have been already tested and be sure that they will work on the satellite. So when you're designing the CubeSat mission, it's better to focus on the strength and focus on the goal of the mission and to leave the rest for others. I would like to ask if you have any questions until now. Is everything clear or?
Yeah. Questions do you have? So I think for now is okay. I think they are keeping their questions till the end.
Till the end. So do I understand correctly that the lecture is until 1, right?
Again, sorry, lectures?
So the lecture until 1.
Until 1. Okay, European time. Yeah, you have.
One more hour.
Yeah. But you can finish earlier if you want. So there is no problem.
Okay, so we can make maybe 5 minutes break, and then there will be.
Of course.
The last part.
Because even the professor from Sofia, she asked 15 minutes. So because they used to 40 minutes lectures, 10 minutes break. That's kind of how to say.
The standard.
Yeah, some kind of standard. Okay, no problem. If you want some break, it's okay.
So yeah, so before the next part, we can make it 10-minute.
Yeah.
Okay. Yeah.
Thank you. So again, 10 minutes break, and we will start at 4. Sorry, it would be 12.
Yeah. If you have any questions, please put them in the chat, and we can address before the next next round. Yeah. Thanks.
Okay.
All right. Then next topic would be the history of CubeSat missions, and starting from 2001 year until today. A few words about major events in the timeline of the CubeSat missions. 1999, the first publication of CubeSat standard was released. The first CubeSat was launched in 2003. In 2004, there was a code of conduct of space debris mitigation was accepted, and this included these 25 years of orbital decay for satellites. 2014, the first Dove satellite with the biggest constellation of CubeSats was launched. 2017, the launch of 104 CubeSats at one rocket at once occurred. So the real innovation was not only the standardization of the satellite, but in the separation system. So the container, which is qualified and flight proven, and can be installed on the launch vehicle, has many other benefits besides like just reducing these risks. Still, the approach is pretty effective, but only until a certain size. This is why there are not so many CubeSats bigger than 16 units. In other words, the fact that there is a separation system which is handling all the mechanical, electrical, vibration interfaces to the launch vehicle significantly reduces the risks for the small satellites in terms of this like interfaces match and launch environment. And let's have a look on some of the pretty cool CubeSats which have been launched before. So this is Day-4 satellite, was built by University of Tokyo in Japan and launched in 2003 by Eurocat launcher. It was dedicated to pretty high orbit with 820 kilometers sun synchronous. The basic, that was one of the like pretty much first CubeSats launched into space. The platform was based on all the components were commercial on the shelf. As for attitude control system, it used permanent magnets and hysteresis rods. And it also used some CMOS camera module for taking pictures of the Earth. The fun fact with the permanent magnet is that in the magnetic field of the Earth, it can, the magnet can orient the satellite without like really turning on and off the attitude control system. So it's a really cost-efficient way to orient the satellite in the position you want. So the fun fact about the satellite is, even though it was launched in 2003, it's already 17 years on orbit, yeah, like 14 plus years on orbit, and it's still operational. Yeah, so it's the camera module, which was installed in the satellite, like pretty small and pretty compact camera. And these are the pictures taken with this camera. Yeah, like pretty low resolution, but thinking about like 17 years back, that was like the big success for such a small CubeSat to make these pictures. The next interesting satellite is QuakeSat-1. It's built by Stanford University and operated by QuakeFinder LCC, and launched also with the previous satellite in June 2003 to the same orbit. As for the mission, it was single axis search coil type magnetometer, like pretty interesting device to verify for detection of extremely low frequency waves for earthquakes, and that's basically where the name of the satellite comes from. So it cost of the satellite was like 1 million, pretty high cost if we looking at that today. That was the first 3-unit CubeSat with deployable solar panels and a scientific payload. So it worked more than 11 months. It was pretty expensive to operate. That's basically was the reason behind shutting down this the mission. If you look on the left, you can see some like how the satellite deployable structures were installed on the satellite. So that's the body with the mounted solar panels. So it had quite a large area covered by solar cells. This is the inner frame with hardware components, and it was installed like it is supposed to be inside the body mounted. After that, there was antenna assembly for telecommunication and telecommand, which was like installed on the boom. So if you can imagine this green rectangle inside the satellite, so the antennas were already boomed, so they were a little bit further from the satellite body. Then there was another boom extension with the magnetometer payload. So in order to operate magnetometers properly, there shall be no like magnetic disturbances around this. So it's, most of the magnetometers which are used in CubeSats and the satellites are built on this kind of booms to place them further away from structure and from some like noisy components as reaction wheels, for example. So that was the reason behind this boom extension and yeah, magnetic payload. That's how the satellite looked like in the real life. So that's the antenna, the satellite with solar panels, the boom, and the magnetometer in the end. GeneSat-1 was developed by NASA Ames Research Center, was launched in 2006 by Minotaur rockets to 410 kilometers, 40 degrees inclination. The main mission goal was to onboard micro laboratory that provides life supports for bacterium. So basically it had the compartment where some bacteria lived with some specific environment inside. That was the first successful mission which kind of combined bus module and dedicated payload. So they were like quite a tricky interconnection between them. So flight ready autonomous technology demonstration farm platform that became a platform for some other like solutions as FarmSat, NanoCLD, and so on. That was the first CubeSat which was able to regulate internal payload compartment temperature within like plus minus 0.5 degrees Celsius. And the payload consisted of 12 well-fluid plates that used 12 custom optical units and growth rate measurement. Basically, so the bacteria inside this compartment had like their very comfortable for their development environment, and the growth of the bacteria was measured. Yes, here there is one more representation of the satellite. It's like a 3-unit CubeSat with solar panels around, with some tuna can outside. The bus module occupied only like 1 unit of the satellite, and the payload module was in the rest of the 2 units. Here you can see the golden cover of this unit, and this is the unit without this cover. The next one is Delphi C3, was built by Delft University of Technology, Netherlands. It was launched in 2008 by PSLV to 630 kilometers sun-synchronous orbit. The point of this mission was to test wireless sun sensors, a new type of thin film solar cells. In this kind of small satellites, sometimes it becomes tricky to place the harness and to design the harness in a smart way that once satellite is integrated, all the cables are nicely placed and there's no collision and there's no risk of cable being detached. That's why like some of the CubeSat developers thought towards making some sensors wireless, and that was one of the first satellites to show the technology. First, so this satellite was first university class sat of Netherlands. After the satellite was launched and was functioning, the students of this company, they decided to build the company out of that, which is still in the market. It's called ISIS. And now it's running in the CubeSat shop. So basically it's an online shop where you can buy components for the CubeSats. Many of the components of this satellite are successfully commercialized and been developed. So that's like another render of the satellite. Here we can see that it has like pretty tricky solar panel design. This is built of this thin film solar cells. It has like quite a lot of antennas. Yeah, it's an interesting design. This is the autonomous wireless sun sensor board, as it's requires no cables, which means no power. It carries their own solar cell to get some power. With a mass of 75 grams, it occupies quite a lot of space for the sun sensor. So it's 6 to 4 to 2 millimeters. As for comparison, our sun sensors occupy like 1 by 2 by 1.5 millimeters, cube millimeters. Field of view was 90 to 90, which is also kind of not the best quality sun sensor. There are much better sun sensors in the market, but the fact that it was wireless was pretty cool. So it used radio link based on commercial modules of 915 megahertz. It carried 2 sensors on one board, and as one failed, another one was working and was functioning, so the mission was successful in the end. So the miniaturized version of this module was under development, but I actually didn't see much of the sensors like that in the market due to the fact that building the wireless network with every component carrying its own solar cell is actually more difficult than building the proper harness for the satellite. This is the BSAT 1 and 2, the satellite developed by Technical University of Berlin. It was launched in 2013 on PSLV. So the first one launched in 2009 on PSLV, and the second one launched on Soyuz in 2013 on sun-synchronous orbit of 730 kilometers with a mass of 1 kilogram. The main mission was to demonstrate the technology developed at the university. So these were the first satellite to demonstrate active attitude control within the 1 unit form factor. For that, special micro wheels developed by for this mission were built by the Astrofine company. So they were like really small. I'm not sure. No, there's no picture, but they were occupying like 0.5 space of the satellite, and the rest was for like onboard computer electrical power system. Yeah, that's the picture of the satellite. Every side of the satellite was carrying solar panels. These are the 2 antennas. Sun sensors were placed around the solar panels. Yeah, that's pretty much it. This is the next generation called BSAT 4, was built and launched in 2016 to 500 kilometers orbit. The main goal was also technology demonstration, and there the major goal was to prove the concept of GPS-based orbit tracking. The satellite was based on some modifications of the previous version of the BSAT. However, there was like additional space, like on the top here you can see the GPS antenna. So there was additional space to accommodate the GPS receiver built by German Aerospace Agency. A few words about DOF satellites. So I named the Planet Labs company several times earlier today. The first satellite was launched in 2013 by Soyuz to 550 kilometers sun-synchronous. The main mission was to demonstrate the capabilities for the remote sensing. So that was one of the first satellites, the first satellite launched by Planet. That was the prototype of the next Flock constellation, which has been launched since then and has achieved more than 400 satellites on orbit. So the overall size of the satellite is occupied by 3-unit camera and the telescope. This is the X-band transmitter with antenna for the payload data link. Now, with this use of this camera, it's possible to achieve 5 meters resolution, spatial resolution. Satellite carries also deployable solar panels. And the tricky thing about the architecture of the DOF satellite, as all the size of the CubeSat is occupied by telescope, which is like cylindrical, all of the other components are located like around them. So they are not standard PC104 style of PCBs. They're like really interesting oval size design. In order to provide this flock constellation and in order to achieve this idea of daily revisit of single point of the Earth, it requires to build like a facility where several satellites can be produced per day. So daily global coverage capability is the unique selling point of the company. And here you can see like how many of these satellites are getting ready for the next launch. Every satellite is around 5 kilograms, and for active attitude control, they're using flywheels, not direction wheels. Expand downlink and UHF uplink are used for commanding the satellite and downloading the data. Lemur satellite, built by Spire Global, is the next interesting example of the CubeSat 3-unit form factor. It was launched in 2014 to 650 kilometers sun-synchronous orbit. The primary goal was to demonstrate the technology. So that was the first satellite launched by Spire Global, and like this platform became the basic for the whole constellation, even though other satellites were carrying different payloads. It's called Lemur because the idea behind the satellite that satellite opens the solar panel as the lemurs are staying on the sun. Pretty fun fact. And every satellite weighted like 4 kg, had 3-axis active attitude and orbit determination control system. X-band was used for communication. So primary goal of this constellation is to track ships using ICE signal. This is the possible application of that is trade monitoring, asset tracking, CNR, illegal fishing, and everything like in maritime domain, privacy awareness. Up to date, Spire has grown the constellation to more than 50 satellites and providing their service in this field. More exciting applications, the NASA IceCube, developed by NASA Goddard Space Flight Center, was launched in April 2017 by Cygnus to 400 kilometers orbit for technology demonstration, with primary goal to validate sub-millimeter wave radiometer for cloud ice observations. So basically, weather monitoring. This is the internal configuration of the satellites. So solar panels, deployables. Then the core sun sensors. Here, a radiometer payload was accommodated on the side of the satellite. The main stack is located in the middle. With some like interface module, GPS receivers. We can see 2 UHF antennas, the radio module, electrical power systems, the battery pack, and GPS antenna patch on the side. And total mass was 3 kilograms with the size of the 3U. As for attitude control, flywheels were used, and here the satellite didn't have high-speed communication, but used the UHF to downlink the data. So basically, the satellite was built on the Pumpkin-based components. That's another company providing CubeSat components, while like some other components were purchased from like different vendors. That's a good example of how the company is not building the platform by themselves, but buys different components and just integrates the bus together. RainCube is an awesome project developed by NASA Jet Propulsion Laboratory, launched in 2018 for LEO mission. The main goal is to demonstrate the technology or Ka band atmospheric radar for CubeSats in the space environment. So basically, this is the huge Ka band antenna, and yeah, the idea is to use this antenna for atmospheric radar applications. Yeah, here we have the satellite. This is the spot where antenna is located during the launch. Basically, it's deployed like an umbrella once on orbit.
Sorry, you turned off your demonstration.
Okay, sorry. Thank you. Just a second. Shall be fine right now.
Yeah.
Okay. Right. So the antenna is deployed as an umbrella after the separation of the satellite. So it's just opens right here. We can also see several like star trackers, batteries located here, and huge solar panels for this antenna to be able to function. As NASA is the one who is leading the CubeSat technology evolvement in the world, there are a couple of other pretty cool projects which have been launched. Aerocube, for example, and OCSD. There were 2 satellites, and the third satellite was launched recently to demonstrate optical communication between satellites. The first 2 Aerocubes failed due to attitude control system imperfections. However, the third one was already functioning and could downlink quite a lot of data. CPOT is a mission to demonstrate in-orbit rendezvous and proximity of 2 CubeSats. Basically, 2 CubeSats, first of all, shall position themselves in the orbit so they can dock and then demonstrate the docking mechanism. ISAT, this is the CubeSat with propulsion based on Hull technology, while the satellite size, as we have noticed in the statistics before, satellites and CubeSats are becoming bigger as the instrumentation grows and people would like to launch more interesting and more advanced satellites on orbit. For some of them, it's already required to keep the station to be able to change the attitude or to keep the orbit during the timeline. So some of the propulsion technologies, for example, Hull technology, is really interesting when we're talking about the CubeSats. Pathfinder TDR, that's the 6U CubeSat model for the big satellite bus, which can be used for multiple technology validation missions at the same time. All right, so these were some exciting examples of CubeSats, and now I would like to dedicate the last part of my talk to some launch vehicles and some rockets description. And I'll start with deployers in general. So there are a couple advantages of using deployers on orbit. First is standardization. This allows to choose from different multiple deployers without changing satellite mechanical properties. Basically, all the deployers which are in the market, they follow the CubeSat design specification, and it leaves the flexibility for satellite providers to choose the best option in terms of deployment. They are spring-based. Deployment mechanism is based on spring, so it's smoothly and really reliably. So this fundamental physical principle that contributes to easy and safe deployment. So there's no pyrotechnic, it's just spring-based. Different launch opportunities, so deployers can be used on all the launch vehicles, which is providing pretty wide range of launch possibilities for customers. The flight heritage includes that like flight proven deployers are reliable and don't have to be modified. So after one time working on orbit, you can be sure that it's like quite reliable. Safety is the next characteristic. So the total enclosure of the CubeSat reduces safety concerns coming from the side to the launch provider. Here, what we've talked about was the mechanical vibrations make it, as the deployer dampens the mechanical vibrations, it's much safer for the CubeSat to be launched using this dampening interface. And of course, like less work. The amount of documentation which shall be provided to the launch provider is quite big, with all the like meeting all these paper requirements is quite a big piece of work. So while choosing the deployers as an option to go to like orbit, it will just take most of this documentation away and much less get paid from that. And here are some, let's talk a little bit about the rockets and the launches. The first one, and the one we've had the most experience with, the Soyuz, with the main stage frigate. It's flying since 1966 for quite a long time, and frigate stage is since 2000. Yeah, it's like the basic payload masses to sun-synchronous orbit can reach 4.8 tons. And if we're talking about LEO, it can reach up to 8 tons. It is quite cost-effective. In terms of successful launch and possible orbits, it's also a pretty good choice. However, it's not as frequent as some satellite providers would dream about. The PSLV is an Indian rocket developed by Indian Space Agency. It's working since 1993. It has much less payload capacity as compared to Soyuz, only 1.75 tons per sun-synchronous orbit and 3.8 tons for LEO orbit. It's pretty cheap, which brings to the backside of, there were a couple of big launch failures, so successful launches, like we put 2 out of 5 grade here. It cannot go to any possible orbit, and the launch frequency is quite low. However, that like the biggest satellite, CubeSat, amount of CubeSat was launched with this Indian rocket was like 104 satellites at the same time. Vega is the European orbit developed by IVO and Arianespace. It's been in business since 2012. It can carry even less mass to the sun-synchronous, only 1.45 tons and 2 tons to LEO. It's got quite not cost efficient, and it had like a lot of troubles with successful launches. Like there were quite a lot of launch failures, especially within last years. There are several orbits it can deliver the satellite to. However, the launch frequency is like absolutely low. Falcon 9 is the US company. I think like everybody knows about SpaceX, and it's launching since 2015. It can bring to low Earth orbit up to 22.5 tons, while the cost like is getting lower and lower every year. So it's quite cost efficient rocket. There are many successful launches, like put out 2 out of 5, including the cost failures at the very beginning. But I think right now it's quite a reliable rocket. It cannot do as many possible orbits like as like others can do, but it's absolutely beautiful in terms of launch frequency. That every year SpaceX is like launching more and more rockets, especially with the technology of bringing the rocket stages back. Comparing to the existing and like big rockets, there are a couple of other small launchers which are coming, which are already working. So first one is the Electron by Rocket Labs, the New Zealand company. They can bring in up to 150 kilograms to sun-synchronous orbit. So they had like already more than 10 launches as far as I remember, and they were properly functioning. New Glenn is the Blue Origin development. It's still in the development. It's a successor of New Shepard and suborbital crew flights. News are coming, but yeah, they're still in the test procedures right now. Firefly Alpha is the 400 kg US-based LEO orbit. The unique selling point of this rocket is that it has light carbon structure. I mean, the development is a little bit paused. We'll see what will be in the future. And the Ripple Aerospace, Norway-based company. The interesting fact about this rocket is that it has a chaotic start. So basically you can bring the ship anywhere to the equator or to any other place and launch from there. Talking about launchers, there are many more launchers, and I think in Europe, almost every country wants to develop their own launcher. However, that's a tricky question. Like, there shall be several tens of hundreds of millions investment before the proper engine and the proper rocket is built. And last topic I would like to address today is regarding space debris. As people become more and more aware of what's happening in the low Earth orbit and how many constellations are there, space debris mitigation was issued by United Nations in 2002. So these guidelines, they recommend that the satellites and like everything what is designed shall be deorbited within 25 years after end of life. However, this 25 years, if we're talking about hundreds and hundreds of satellites launched by year, is quite not enough. CubeSats in orbit above 550 kilometers have orbital life of more than 20 years in general. If we conduct like the simulation of decay, we'll see that it can be like much bigger. So taking into account the amount of satellites launched within the next 20 years, the orbit can become like really crowded. So what are additional aspects here to think about? The lack of the propulsion and propellant for mitigation maneuvers. That means that not every CubeSat developed carries the propulsion units. Most missions do not require that. And short design time and long time without any control, as some CubeSats are failing. Some CubeSats just like after the mission has been conducted, nobody takes care of the satellites which are not interesting anymore. As a consequence, forced deorbiting might become the mandatory in the near future, at least. Like space agencies are talking about that, especially in the European Space Agency, as they're pretty concerned about like space debris. That might become the requirement for the satellites to be launched to carry some additional instrumentation to be able to deorbit within like lifetime or even faster. There are mechanisms to deorbit which can be integrated into small satellites. The first one is the drag. This mechanism can have an impact only below a certain height. So a small CubeSat cross-section limits maximum orbit height. This can be done like with a huge sails over the balloons, basically increasing the drag. The atmospheric drag satellite can decay faster. Electrodynamic tether can use the magnetic field as drag forces. This can be done like basically on many other orbits. However, it's not as efficient as this drag sails, and propulsion is the most efficient mechanism for lowering the orbit. It is used to force reentry processes by changing the orbits, like making the orbit lower. Low orbit maintained by constant propulsion will also mitigate the failures in the low, like bring it to fast deorbiting. Yes, let's review some of the deorbiting mechanisms a little bit more precise. So this is the so-called CubeSat terminated tape. It's a small compact device which is placed on the side of the satellite. It's quite lightweight. And it helps the satellite to deorbit with this tethered mechanism. It only weighs 83 grams, and it's also equipped with solar cells, which means it's self-sustainable. It doesn't need any connection to the satellite avionics. Balloons is the next one. So they're inflated by the command from the CubeSat as soon as it's time to deorbit. So there are several developers of this kind of devices. They weigh much more than these tethered devices. For example, this one is more than 150 grams. There are different diameters. As for material of the balloon, a silver aluminum oxide coated capiton is used, and it's impregnated with rigidizing resin. So it's quite weird to see this the satellite with such a huge balloon. Yeah, but this kind of devices would really help to mitigate some debris in the low Earth orbit. And some propulsion modules. For example, this one is developed by Aerojet Rocketdyne. This is already the big device to be carried by the CubeSat, 1.7 kilograms without fuel and 2.2 with fuel. As for size, it occupies more than 1 unit space, and it uses you can see which propulsion it can use. The maneuver, which is which could be done to deorbit the satellite, is quite complicated, and it requires the advanced attitude control characteristics for the spacecraft. And as we can see, this propulsion module cannot be accommodated in the small CubeSat already, which is the limiting factor for these types of deorbiting mechanisms. And this one is actually my favorite type, the huge inflatable sail to augment the drag force and this maybe solar pressure force as well to deorbit. These types of sails have been already on the orbit. The technology readiness level is quite close to 9. And this one in particular is developed by SSTL with a mass of 2 kg. It occupies less than 2 units, but it can, once deployed, it's taken 25 square meters, which can, from 550 kilometers, can take 2 years for the satellite to deorbit. As for material, the 12 micrometer capiton membrane with aluminized structure is used. And here we can see the sail during the test. Quite big. And this is this is just a small satellite which is carrying this module. All right, so that was pretty much it from my side. Do you have any questions? I will be happy to answer.
Thank you very much. So here was some question about P-pods.
Mm-hmm. Rails. So the rails for the CubeSat. Yes, so basically they have to be manufactured and designed by the satellite developer. However, while developing the CubeSat, it's normally people contact deployer providers on the early stages, and like deployer providers and launch providers can assist with these requirements and can help designing the proper structures. So for example, at ExaLaunch, we do this kind of service. Yes, any other questions? No.
And I have a question about how can we, like universities, can be involved with such kind of projects. So how could be possible to sharing tasks, for example, making some research, or even for publications, like starting jointly projects on writing some articles.
Mm-hmm. I think I'm not sure when she is presenting, but there is another lecturer, Yelena. She's more in charge of contacts and all the collaborations. So I think she is the best person to address this. Like I'm more on the technical side.
Yeah, I mean, like from side of the researcher, what do you think? Could we be involved also, or it's restricted?
I think for universities, it's like for aerospace related or focused universities, like CubeSat field is the best to start doing some kind of research. Yes, it's like it's not as complicated as traditional aerospace projects. It's pretty easy and pretty cost effective. So yeah, sure.
Okay. Thank you. Is there any other questions? So, okay, if there is no questions, Nurdanega, do you want to say something? So we have specialists on space technologies who started already the master courses. Okay, I think some technical problems. Okay, so I would like to say very, very big thanks for your time and for your very interesting presentations, and we'll wait for them for your slides.
Mm-hmm.
And is it possible to put them on the websites, like for public?
Like from my perspective, there's no problem. I will just need to consult with organizers of the school.
Okay, okay. And if you'll share with us, I will just share with others because I have a list of emails.
Yeah.
Yeah, okay, thank you very much. And
thank you too.
Good luck. Okay.
Yeah, it was a pleasure. Thank you very much for your attention.
Thank you. Рахмат хамаге, спасибо большое всем.
Thank you very much. Bye-bye.